All right, so continuing to use the different trig functions, brings us to the reciprocal identities, which we discussed sort of when we talked about the definitions for cosecant, secant, and cotangent. But reciprocally, meaning they're flipped over fractions of each other, there is a relation between pairs of the different trig functions. So a reciprocal identity is a relation between two trig functions where one is the reciprocal of the other. Thus, it's called the reciprocal identity. So we can define all of these. Sine is the same as 1 over cosecant. So sine and cosecant are reciprocal to each other. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals. And then vice versa. If I had cosecant, its reciprocal is sine. Secant reciprocal is cosine. And cotangent reciprocal is tangent. These 6 definitions are liable to be a part of your next formula quiz. So it's definitely something that we need to have memorized. Okay. I got ahead of myself. Inverse trig functions will be something we do in this class, but it's honestly in chapter 2. But what I want you to realize is when I'm asking you to do a reciprocal identity, I am not asking you to take the inverse. These are 2 different concepts, even though they look or sound like they should be the same thing. A reciprocal is a flipped over fraction, while an inverse is an actual function that undoes a different function. So these things are not the same as taking the reciprocal. So don't use this cosine of -1 symbol. That is for an inverse trig function, not a reciprocal. Okay? These are not the same thing. Inverse trig functions we will use later. Reciprocal trig functions are just defining the definitions by flipped fractions. But if we know that they're reciprocals to each other, it actually makes solving some of these problems ridiculously easy. Part A says, wants you to find, cosine of theta, given that secant of theta is 5 over 3. But here's our hint here. Cosine and secant are reciprocals. So if secant is 5 over 3, what is cosine? That's it. If we know that they're reciprocals, we don't have to do any other work other than flipping that fraction to its reciprocal, since those functions are reciprocals of each other. Part B says, find sine of theta given that cosecant of theta is -12 over 2. Negative square root 12 over 2. Well, before we really do anything, I'm going to take this value right here and I'm going to reduce that, wow, I forgot all of my words, fraction, and that radical. So if I were to take 12 and break it down, what does 12 break down to? 3 and 4. What does 4 break down to? 2 and 2. So if I were going to simplify this radical, it would have a pair of 2's that pop out and a singleton 3 that stays underneath the radical. So I'm going to redefine cosecant of theta as -2 square root 3 over 2. So I want to use reduced radicals. What's going to happen with that 2 and the 2? They cancel out. So really cosecant of theta is just negative square root 3. I want to find sine, and now that I have a reduced fraction, all I need to do is use this number's reciprocal, since cosecant and sine are reciprocals. So sine of theta would just be the flipped over version of negative square root 3. When I flip it over, that means that there is now a 1 on the top and a square root 3 on the bottom. But if you remember what we learned about last class is we're not allowed to leave square roots in the bottom. What do? Multiply it by itself, square root 3 over square root 3. It's like multiplying by 1, which then means that this would end up being negative square root 3 over 3. So sine of theta equals negative square root 3 over 3. It's still just as easy as flipping that number over. The number we got this time was just required a little bit of TLC instead of just a cute 3/5 and 5/3. So the reciprocal identities allow me to do a lot with these functions with very little information. We kind of touched on this last class when I just told you to flip all of those numbers over, and that's again because they are reciprocal values of each other. Now we get to discuss the signs and the ranges of these functions' values. There's a whole little blurb right there for you, but the main idea here is that different quadrants around our graph have different signs for your different trig functions. If you took my pre-calc class last year, you might remember the acronym we used. I think Ms. Howard used a different acronym if you had her, but it's the same acronym. All-Star Trig Class. I think she used All Students Take Calculus. So either way, that acronym is going to help us remember which of the trig functions are positive in which quadrant. So in quadrant 1, it says all functions are positive. So all sine, cosine, and tangent, secant, cosecant, and cotangent will be positive. In the second quadrant, because of the S, it means sine and its reciprocal cosecant are the only ones that are going to be positive. In the third, because of the T, that means tangent and its reciprocal cotangent are going to be positive. And in the fourth quadrant, cosine and secant, its reciprocal, are going to be positive. All-star trig class. All students take calculus, however you remember it. So this is helpful to help us know what trig function should be what sign. It's a great check at the very end to make sure you didn't accidentally use the wrong sign. So it says to determine the signs of the trig functions of an angle in standard position with the given measure. I also want us to sketch what this angle looks like so that we know what it visually looks like in the quadrants. So 87 degrees, if I were to sketch that, what quadrant should it be in? The first one. So it's going to look something like this. This is 87 degrees. We know it's there because it's less than 90. So we need to determine the signs of all of the 6 trig functions. Since this is in quadrant 1 is my all quadrant, which means if we were to find sine, we'd say it's positive. If we were to find cosine, we'd say it's positive. If we were to find tangent, again, we'd say it's positive. The same goes for all of the reciprocals. Cosecant positive, secant positive, cotangent positive. That makes sense? Okay, I already want you to try some on your own because it's pretty simple. You have B and C to work on your own or with people at your table. Sketch what the angle looks like so you know what quadrant it's in, and then determine whether the 6 different trig functions are positive or if they're negative. You have both B and C. As a quick check, I'll give you more time on C. 300 degrees should look something like this. It's more than 270, but less than 360, so it's 300 degrees. Is that the quadrant that you drew it in? That quadrant is quadrant 4. And in quadrant 4, because of the C there, I know that of the 6 trig functions, cosine and its reciprocal are the only ones that are going to be positive. So if I write out all of them, give a plus sign to both cosine and secant, the rest of them should be negative. Did we get that? Okay, I'm going to give you more time on C in case you need to think about how to draw negative 200 degrees. Okay, what does negative 200 degrees look like? Since it's negative, it should be going clockwise from the standard position, and 200 degrees would make it look something like this. Negative 200 degrees. So that means we are in quadrant 2. In quadrant 2, what are the trig functions that are positive? Sine and its reciprocal, which is cosecant. Everything else should be negative. So positive angles go counterclockwise, negative angles go clockwise. Hopefully we remembered that, or now remember it. It's something we should know. Now, what All-Star Trig class also does for us is it allows us to determine what quadrants angles are in when we're given different pieces of information. So, for example, in part A here, in identifying a quadrant, we are told that 2 pieces of information, that sine of theta is greater than 0, which means sine is positive, and tangent of theta is less than 0, which means tangent is negative. We're going to use both of these pieces of information to determine which quadrant this angle is in. I like doing it this way. there's plenty of ways to think about this, but I draw myself a nice coordinate grid with the all-star trig class listed. We're going to circle the quadrants where the information we were given occurs, and then we're going to see where those two circles overlap. So the two quadrants where sign is positive is the first quadrant and the second quadrant. The two quadrants where tangent is negative, meaning I don't want tangent to be positive, would be these two quadrants. Because tangent is positive in quadrant 1 and in quadrant 3, I'm going to circle the other two so that it can be negative. Where do the two circles overlap? They overlap in quadrant 2, so we can guarantee that the angle we are working with is in quadrant 2. See how we eliminate things and we look for the overlapping? Now what about B? Given the two pieces of information here, number one, that cosine of theta is less than 0, which means negative, and that secant of theta is less than 0, which means negative. Now we need to take a second and think about what secant is the reciprocal of, since all-star trig class doesn't use the reciprocal definitions. What is secant the reciprocal of? Cosine. So when we go to do this information, if we do all-star trig class, we know that cosine is negative in these two quadrants, number 2 and 3. And then we know that secant, which is the reciprocal of cosine, is also negative in those two quadrants. So we couldn't nail it down to one based on the information we were given, so we answer with both. We say it is either quadrant 2 or quadrant 3. Most of the time you'll be able to eliminate it down to one possible quadrant, but if the information overlaps, then we just say, well, it's going to be in quadrant 2 or 3, one of those two. Fabulous. So ASTC is going to be very, very helpful for you to know which quadrant you're working in and whether the trig function you're given should be positive or negative. Now we can discuss the ranges of these trig functions because it's important to realize when you get an answer like out of a trig function, whether or not it's reasonable or unreasonable. Now the range for sine is from -1 to 1. The cosine is from -1 to 1. So these two are the same. If we box these up with things that are the same, we're going to do it like this. So sine and cosine have a range of -1 to 1, which if you have taken pre-cal before, you think about the shape of those waves, it's going to oscillate back and forth between -1 and 1. Their reciprocals are the flipped versions of those. If you took my class last year, I called them the bowls. So we had a bowl that faced upwards and a bowl that faced downwards, but nothing occurred in that little middle section, which means the range of cosecant and secant, the opposite of sine and cosine, is from -infinity to -1 and then from 1 to infinity. So the bowls are shaped different directions. Tangent and cotangent have the same range, and it's all real numbers because their little squiggly S shapes go all the way down and all the way up. Again, kind of leaning on that previous knowledge of what those shapes look like. If you're like, Miss Quigley, I don't know what you're talking about, we will get to the graphs later in this class. But if you kind of group those two things together, there's really only 3 ranges you have to remember since some of them share the range. But knowing this range, again, is going to let us know if we got a reasonable answer or not. So for number 4, part A, it says to decide whether each statement is possible or impossible. Sine of theta equal 2.5. Is that possible or impossible? Well, we know that the range of sine is only between -1 and 1. Is 2.5 within that range? No. So this is going to be impossible. Because 2.5 is outside of the range of -1 to 1. Visually, what this means, that's a terrible straight line. Let me try again. Okay. That sine on a number line, if we were looking at the range, would be in this section from -1 to 1. Well, 2.5 is out here. 2.5 is not in the shaded region for my range, so it is not possible for me to get 2.5 as an answer to sine of theta. I'm not going to draw this number line for all of these, but this is what I'm doing if you didn't understand where I said yes or no to. How about for tangent of theta equal to 110.47? First, we think about the range of tangent. The range of tangent is from negative infinity, that's an 8, okay, just wrote that sideways, to infinity. Is 110.47 within the range from negative infinity to infinity? Yeah, so this one is possible. Last but not least, we have secant of theta equal to 0.6. We think about the range of secant, and we discussed earlier that it is one of the bowls that leans outwards outside of the max and min of sine and cosine. So is 0.6 in the range? Is 0.6 between negative infinity, negative 1, or between 1 and infinity? Oh, that was not a confident no. Okay, we draw our number line just to be sure. So here's negative infinity, here's infinity. We'll say that this is negative 1 and that this is 1. So our range is all of these values here. Where does 0.6 belong on this number line? In the middle. Is that where my range is? No, so we'd say that this is impossible. So these problems are pretty easy, but if you get confused on where that number lies on a number line, it is very nice for that visual to see where it lands and whether it's in the range or not in the range. Okay. Now, we're going to go back to kind of a question we did last time where I want you to find all of the trig values. But I'm going to give you different pieces of information, which means you have to use different pieces of information to find those 6 values. When we were asking you to find all 6 trig functions, the bottom line was that I needed you to find an x, a y, and an r. If we can find x, y, and r, we can write all 6 trig functions because they're just ratios between x, y, and r. So let's work to make sure we know them. It says that angle theta is in quadrant 2. Okay, that's important. We're going to hang on to that. And sine of theta is equal to is equal to 2/3. If this 2/3 represents sine, based on the definition, I know that this is the y value and that this is the r value. So I have a y is equal to 2 and an r is equal to 3. That's all I'm given though. We need to find the remaining value. So if we use Pythagorean theorem like we did last class, which is a squared plus b squared equal to c squared, or x squared plus y squared equal to r squared, we would have x squared plus y squared, which is 2, equal to 3 squared, because that's c. We can solve for x here, really pretty simple. This is going to be x squared plus 4 equal to 9. Subtract 4 from both sides, that would be x squared equal to 5. Take the square root of both sides, and then we get to a problem, because when we take the square root of both sides, you take a square root, you have to put plus or minus. It's either positive root 5 or negative root 5. Knowing that it told me that this function or this angle is in quadrant 2, should that be a positive root 5 or a negative root 5? Two ways to think about it. Number one, if you think about an actual coordinate, if we know we're in this quadrant 2, is my x values positive or are they negative? Negative. We were finding an x value, so which one should we use? Negative. So we know that this is actually going to be negative root 5 due to the fact that it's in quadrant 2. The other way to think about that is the only trig functions that should be positive are sine and its reciprocal, meaning any of the trig functions that use x have to be negative since sine was positive. So once we found out all of those 3 things, we can write all 5 trig functions. We'd say that 6 trig functions. Sine is 2/3. Cosine is negative square root 5 over 3. Tangent is 2 over negative square root 5, which we would rationalize to be negative 2 square root 5 over 5. Cosecant is the reciprocal of cosine, which is just 3 over 2. Secant is the reciprocal of cosine, which is negative 3 over root 5. Oops, gotta rationalize that denominator. Negative 3 over root 5. Negative 3 root 5 over 5. And cotangent is the reciprocal of tangent, which is negative root 5 over 2. I do a quick check at the end. I know it's in quadrant 2, which means the only trig functions that should be positive are sine and cosecant. If we look at all of our answers here, are the only ones that are positive sine and cosecant? Yeah, we have a positive, negative, negative, positive, negative, negative. So we did a double quick check to make sure we realize that only sine and its reciprocal should be positive since it's in quadrant 2. So it's just building off of what we did last time because now you have to determine positive or negative values. Again, if you took my class last year, you'll realize that there are even more identities when it comes to trig functions that we need to know and have memorized, including your Pythagorean identities and your quotient identities. Those of you who have not taken this class before, I know this is a lot. You're going to hang on to it, you got it. This is why I have you memorize things, because then it's already in your brain. Your Pythagorean identities come from the fact that they were determined by Pythagorean theorem. We know that Pythagorean theorem has squares in it, so these are the formulas with the squares. That's how I want you to remember it. The first one is an identity. Identity just means like fact or true statement. That sine squared of theta plus cosine squared of theta is equal to 1. Log that into memory. Tangent squared theta plus 1 is equal to secant squared theta. Log that one into memory. 1 plus cotangent squared theta equal to cosecant squared theta. We're going to log that one into memory as well. Okay? Our quotient identities, which are really pretty easy to remember since it's the definition of tangent. Since tangent is the ratio x over y and x is sine and y is sine and x is cosine, tangent can also be rewritten as sine over cosine. Cotangent, its reciprocal, can just be written as the reciprocal of that fraction. These identities are going to come in handy for multiple ways to solve or rewrite trig functions throughout this class. So let's use them to solve a problem kind of like we did before. Now, most of these problems can be solved either like we did, literally just in example 5, or with the identities, which means we have plenty of chances and choices on how we solve problems. It says, find sine of theta and tangent of theta given that cosine of theta is equal to negative square root 3 over 4 and sine of theta is greater than 0. All right, let's think about what we know. We know that if we look at all-star trig class, that cosine is a negative number. How do I know this? Because it gave me a value for cosine that was negative. So the two quadrants where cosine is negative are the S and the T quadrants. It also told me that sine of theta is greater than 0. The two quadrants where sine is greater than 0 or sine is positive is quadrants 1 and 2. Which means we know that our angle is going to be in quadrant 2. So we know that different values will be positive and negative there. We know that sine will be positive, thus tangent will have to be negative. Since we're looking to find sine, we'll do this first, or I'll do this in red so we know we did this first. And we were given cosine. The trig identity that puts together sine and cosine only, not using any other trig identity, is the first Pythagorean identity. The first Pythagorean identity is that sine squared of theta plus tangent squared of theta is equal to 1. I mean, what? That's not what I meant to write. This is cosine. Let's fill in, again, what we know. We know cosine of theta. So if I leave sine squared of theta, and I substitute in the value we were given in the problem for cosine, we now only have one thing left to solve for, which is cosine of theta. Algebra moment. negative square root 3 divided by 4 squared. When you square something that's negative, what happens? Positive. When you square something that is square rooted, what happens? It's not square rooted anymore. When you square root a fraction, you do the square to the top and the square to the bottom. Meaning that this next line of my equation can be written as sine squared of theta plus positive 3 over 16. Do we follow? Negative times negative is positive. Root 3 times root 3 is just 3. 4 times 4 is 16. I can solve by subtracting from both sides. That means I'm going to do 1 minus 3 over 16, which would be 13 over 16. The reason I did that is because 1 is the same as 16 over 16, so 16 minus 3 is 13 over 16. I want sine of theta, not sine squared of theta, so I'm going to square root both sides, which means I have plus or minus the square root of 13 over 16. Similarly to when we did this with squaring it, when you square root something that's big, you just square root the top and square root the bottom. 13 is a prime number, so it doesn't have a square root, but what is the square root of 16? 4. So sine of theta is either going to be positive root 3 over 4 or negative root 3 over 4. Which one?
Negative.
What quadrant are we in? In the second quadrant, should sine be positive or negative? Positive. So we can get rid of the negative sign because we know it's in quadrant 2 and verify that this is square root 13 over 4. There, our little explanation. In quadrant 2, sine is positive. Phew! I found one of the two things it wanted. It wanted sine of theta. I picked to do the Pythagorean identity since that's the thing that wrote sine and cosine in terms of each other with nothing else. If we return to the problem, it also wants tangent of theta. So if I go to find tangent of theta, I want to use one of the identities above that is written only in terms of things we know. If I look at the Pythagorean identity, the one that involves tangent also uses which trig function? Was I given secant? We're not going to use this. Is there another identity up there that only uses things that we know? Sine over cosine. Yeah, tangent is defined to be sine over cosine. We just found sine and we were given cosine. So we can use the quotient identity that tangent of theta is equal to sine of theta over cosine of theta and fill in what we know and just reduce a fraction. That's pretty easy. We can do that. So tangent of theta, which is what we're searching for in this problem, is going to be sine of theta, which we found was square root 13 over 4, over cosine of theta, which was given to us as negative root 3 over 4. Ew, we have fractions in our fractions. What do we do to do this without the use of a calculator? Yes, instead of dividing, we want to multiply, but multiply by what? Sort of. In Algebra 1 and 2, you called it keep, change, flip. Do y'all remember that? You keep the first fraction. You change the divide bar to a multiply sign, and you flip the bottom fraction. That's a negative, but it looks like I didn't. Okay. Those 4s are going to cancel each other out. Pow, pow, they're gone, which means this is square root 13 over negative square root 3. Ew, a radical's in the bottom. How do I get rid of it? Multiply by itself. So I'm going to multiply by square root 3 over square root 3. The denominator is going to cancel itself out, so I would just have 3 in the bottom. And then since I'm multiplying root 13 times root 3, those roots have the same index, so you can combine them together, which just means I do 13 times 3 and stick it back underneath a radical, so that's square root of 39. So tangent of theta is equal to negative square root 39 over... How did I get the 39? I just multiplied these two numbers and stuck them underneath the radical. Yeah. As long as that's like a square root and a square root and not a square root and a cube root, you're allowed to do that. If you're taking different roots, you can't do that. Now let's just double check we got the sign correctly. We said the tangent should be negative. In quadrant 2, is tangent negative? Yes, okay, we're good. You always want to give yourself a quick check on sign because it's the easiest way to miss the problem is just by putting the wrong positive or negative sign. Whoa, pause. Let's think about this one again before we try another one. What are your questions? Where should I go back? Okay, I assume the question that you're not asking is how do you pick which one to start with? Which is a great question. So let's look at the next example to see if we can choose the correct one to start with. In example 7, we want to find sine and cosine. We are only given tangent. Is there an identity up at the top that utilizes tangent and sine and cosine together? Okay, let me rephrase my question because I confused myself with my own question. If we're looking at just Pythagorean identities right now, not the reciprocal, because I obviously know tangent of theta is equal to sine over cosine, but it doesn't work for this problem and a reason I'll explain later. Is there one of the Pythagorean identities that uses either sine or cosine and tangent? No. But I'm going to tell you we are going to use one. How's that possible? I'm zeroing my brain in on this guy because I was given tangent, right? Is there a way I could rewrite this or think about this to where plugging in a tangent value will give me either sine or cosine? Maybe by this. What is secant the reciprocal of? Secant and cosine go together. 1 over cosine. So if I found this, I'd be able to just like flip the fraction over and know cosine. Which means that's going to be a good place to start. These are puzzles that can be solved in many different ways. So we're going to start off with relating, these different colors, cosine and tangent. The reason we're going to do that is because we have the Pythagorean identity that tangent squared theta plus 1 is equal to secant squared of theta, which is the reciprocal of cosine. So if I plug in what I know, based on the problem I was given, I know that tangent is 4/3. If I square 4/3, it means I square the top, square the bottom. This would end up being 16 over 9. And I'm going to add 1, but for my brain's sake, I'm going to rewrite 1 as 9 over 9. Are we okay that 9 over 9 is the same as 1? Okay. That means this becomes 25 over 9 is secant squared theta. And if I square root both sides just to find secant, that means I'm going to have plus or minus the square root of 25 over 9 equal to secant of theta. Well, what is the square root of 25 over 9? 5 over 3, because I can do square root of the top over square root of the bottom. Oh, we got to decide whether this is going to be positive or negative. How do we know it's going to be negative? Correct. It tells me we're in quadrant 3, which means the only trig functions that should be positive are tangent and its reciprocal. So cosine, which is what we're looking for, or secant, should be the positive version. So based on the fact that this is in quadrant 3, we know that this is negative 5/3 for secant of theta. So what is cosine of theta? Just the reciprocal of what we got there. So you can utilize the reciprocal identities inside a Pythagorean identity, which is wild. Now that's great, but I also need to find sine of theta. Now that I have found cosine, is there an identity that uses sine and cosine together so that I could find sine? The quotient rule? Sure. I did it differently in my notes. That totally works. So if we do tangent, here, I'll go this color. If we do tangent of theta is equal to sine of theta over cosine of theta, and we fill in what we know, we were told tangent was 4/3. We're looking for sine, and we found out that cosine is -3/5. What do I do to solve for sine? How do you get sine of theta by itself? Got to get rid of the denominator, which means we're going to multiply both sides by this denominator. That's not right. No, that is right. The 3's are going to cancel each other out. And thus we have that sine of theta is -4/5. The way I did it in my notes, because again, these are all puzzles that you can use different identities for, is I went back and used the first Pythagorean identity, sine squared plus cosine squared equal to 1. When you solve, you end up getting the same thing, -4/5. So however you see it, solve it.
Wait, which one did you use?
I ended up using, so another option here would be to use sine squared, plus cosine squared equal to 1. So I said, all right, well, we'll find sine of theta knowing that cosine of theta is -3/5. Kind of like we did at that first part of number 6. And I ended up solving for the sine of theta. You get the same answer. So however you see it, you work it. Because your brain might see it differently than my brain. As long as you use the identities correctly, you're in good hands.